In previous few lectures, we have discussed in very detail to write down the equation of motion of a particle or of a body in a rotatory non-inertial frame. You have seen how we can write the equation of motion. In other words, you can say how we can apply the Newton's second law of motion in case of a rotatory non-inertial frame. We have seen that when the frame rotates with a constant angular velocity, then apart from the real forces acting on the particle, we need two Coriolis forces acting on the particle to write down its equation of motion. And the two pseudo forces which are needed to write the equation of motion, you have learned, are Coriolis force and the centrifugal force. Now it is application part of this theory, and in first application we will deal with the problem of finding the deviation of a freely falling body under gravity due to the Coriolis force. It means in lower classes when you talk about a free fall problem, then you never think about the deviation of the particle due to Coriolis force, because in lower classes you treat the earth as an inertial frame. But actually, you know, our earth is rotating about its polar axis from west to east with a constant angular velocity omega. And this angular velocity omega is along the polar axis of our earth. So in fact, earth is not an inertial frame, it is a non-inertial frame, okay, because it is a rotating frame. So definitely, if you want to write down the equation of motion of a particle in this rotatory earth frame, or you can say that when a particle will move with respect to our rotating earth, then if your aim is to write down the equation of motion of that very particle, you must take under account the pseudo forces along with the real forces acting on the particle. Here we have to deal with the problem of deviation of free fall of particle or free fall of body due to the Coriolis force. So we will not think about the centrifugal force, we will only think about the Coriolis force acting on the particle or body which is falling under gravity in the Earth's rotatory frame. So you can see this figure. Actually this sphere which I have shown in this figure, this represents the Earth. Okay, O is its center. Although you have definitely a knowledge that Earth is not perfect sphere, it is some flattened at its pole N and S, that is at North Pole and South Pole. It means its equatorial diameter WE, as you can see in this figure, is somewhat larger than the polar diameter NS. It means WE minus NS is almost equal to 52 kilometer. It means the equatorial diameter is almost 52 kilometer greater than its polar diameter. Okay, but in rough calculation we neglect this difference and treat the earth as spherical. So in this problem too, we are treating our earth as a sphere. Okay, and let us see here, this is the point P which is above the earth's surface at a height h. It means I have assumed that this AP is equal to h. Okay, and for calculation we take this point P as origin and let us construct a Cartesian coordinate system here. Actually, the z-axis of this coordinate system is taken in vertically upward direction as I have shown in this figure, or you can say that the z-axis is taken in radially outward direction. Okay, and x-axis is taken in eastward direction and the y-axis is taken in northward direction, as you can see here. Okay, In fact, as the earth rotates with angular velocity omega from west to east, and this angular velocity is directed along the polar axis. So this line which I have marked in this figure, you can see this line is actually parallel to the polar axis. So the angular velocity omega is along this line which I have shown here. And you can see this angular velocity omega of our earth lies in the yz plane. Okay, it means omega is in yz plane, so you can say that omega is perpendicular to x-axis as we have considered the coordinate system. Okay, now the point P from where a body will be dropped, which is at a height h from the surface of the earth, that point is lying at a latitude lambda. Do you know about latitude? Definitely you have learned in your geography class in lower classes that latitude of a place is what? This is actually the angular distance of the place or point from the equator. Equator which divides the earth into two equal hemispheres. Okay. And when you say angular distance, that means the position vector of the point, let us say in this figure, this position vector OP of the point P makes an angle lambda with the equator. Then this lambda is called latitude of this place. And if this place is lying in the northern hemisphere, actually the half sphere between the north pole and the equator, this is called northern hemisphere. This is NH. And the remaining half part containing the south pole, this is called southern hemisphere. So in present problem, I have considered this point P from where a body of mass m will be dropped in the northern hemisphere. Okay, mark it. The point is lying in the northern hemisphere. Actually, when this particle or body will be dropped from point P from rest, then it will accelerate towards the surface of the earth due to the force of gravity, which will act along this direction PA. Okay, this is the vertically downward direction. Okay, and the body will gain velocity, and that velocity is actually with respect to this rotatory earth. And you know, when a body moves with respect to a rotatory frame, then a Coriolis force acts on that body. Okay, so definitely if you are talking about a falling body towards the surface of the earth, the body has velocity with respect to the earth. So in earth's frame, the body will experience two forces. First one is actually real force, which is force of gravity mg. This is actually real force. Okay, a real force. And apart from this real force, this body will also experience a pseudo force, which is called Coriolis force, because the body has velocity with respect to the rotatory frame, that is the frame of the earth. This is actually the pseudo force, which is called Coriolis force. You have already studied it. Okay. And in this problem, we have to find how much the particle will get deviated from this vertical line PA due to this Coriolis force. This is our problem. Okay. We have actually to calculate that deviation. Okay. Now let us try to find how we can calculate this deviation. For this we will have to calculate the Coriolis force acting on the particle. And you know the expression for Coriolis force we have studied in the previous lecture, and I think definitely that expression is in your mind. You know this is minus 2m omega cross v. Actually I have written in earlier classes v dashed, but here I am writing v because here we are talking about the motion of only one particle, and this v is actually the velocity of our particle with respect to this rotating earth, and omega is the angular velocity of the earth. Here earth has been treated as a rotatory frame. So to know the Coriolis force acting on the particle, you can see the expression, we will have to know what is this omega and what is this v. Once you know about omega and v, easily you can find the Coriolis force. And once you know the value of Coriolis force, you can easily write the equation of motion. Okay. And writing equation of motion, we can easily find the deviation of the particle due to this Coriolis force. Okay. So let us see, since omega is lying in the yz plane, so it is perpendicular to x-axis as I have mentioned earlier. So this omega will have two rectangular components. One will be along y-axis and another will be along z-axis. Its x component will be 0, because when you will try to find its x component, omega x, that will be simply omega cos 90, because with x-axis this omega vector makes 90-degree angle. So this will be 0. Now see the geometry of this figure. Since this angle is lambda, and from geometry you can see, then this angle will be also equal to lambda, which is I am marking in the figure. And then as y-axis is perpendicular to x-axis, then this angle will be 90 minus lambda. Again, this omega is perpendicular to x-axis, so this total angle made by omega with x-axis is 90, but this angle is 90 minus lambda, so this angle between the y-axis and omega will be equal to lambda. Okay, angle between omega vector and y-axis, that is northward direction, that will be equal to lambda. So you can say that omega makes angle lambda with the y-axis, and 90 minus lambda will be the angle with the z-axis. Okay, all things, these things I have actually mentioned here, you can see. See, omega, this omega vector in general can be written as omega xi plus omega yj plus omega zk. This is a general rule for writing the vector in terms of its x, y and z components. But you have learnt that x component of omega is 0, so I have written here 0. But omega y and omega z will be not 0, because this vector omega lies in yz plane. So omega is simply equal to what? This is simply omega yj plus omega zk. But see this figure. Since omega makes an angle lambda with y-axis, so its y component will be omega cos lambda, and its z component will be omega sin lambda. So I have written here, you can see omega y is omega cos lambda and omega z is omega sin lambda. I have not substituted this value here. When this will be needed, I will substitute it. Okay. Now we will think about the velocity of the particle. Once you drop the particle from point P, the body gets accelerated due to the force of gravity. And let us consider when it is just to reach the point A, that is on the surface of the earth. Let us say then its velocity becomes v. Its velocity is v. We consider it. It means after dropping from point P, the body attains or body gets or body achieves a velocity v when it is just to reach to the surface of the earth. And let us say the body reaches to this surface of the earth at a time t. We consider it. Okay. So what will be this v? You know, v in general can be written as vxi plus vyj plus vzk. But since our body is moving in negative z direction, this is negative z direction because this upward direction is positive z direction, and the body is moving in vertically downward direction. So velocity lies on z axis, and if the velocity vector is on z axis, its both x and y component will be 0. Only the z component will be non-zero, and since it is in negative z direction, so you can write that this is simply minus vk. Okay, so velocity at time t of our body, which has been dropped from point P, is minus vk, where k is the unit vector along the z axis at any time t. Okay, so in this way you have defined the velocity of the particle at time t with respect to the earth. Actually this velocity is with respect to the earth, which is a rotatory frame. Okay, now you can see that our body has a velocity minus vk with respect to the rotating frame, which is the frame of the earth, and the frame is itself rotating with angular velocity omega. So you know, apart from the real force, which is force of gravity acting on our body, if our aim is to write down the equation of the body, we must take into account the pseudo force, which is called Coriolis force acting on this body. So first of all we will find out the value of this Coriolis force, and you know, I have mentioned earlier that this Coriolis force is given by 2m times omega cross v dashed, but here I have not assumed velocity of the body with respect to the rotating frame v dashed, but I have assumed it v. So you can write this is minus 2m omega cross v. Okay, and you have learnt that this omega is omega yj plus omega zk, and v is equal to minus vk hat. Okay, now find the cross product. You know j cross k. What is j cross k? Definitely you know j cross k is equal to I. So after taking the product by the first term, this will be omega y v j cross k, and j cross k will be I, but since here there is minus sign, so this will be minus omega y v I. Okay, but k cross k is equal to 0. You know, k cross k equal to 0. So the second term will vanish. So Fc is equal to minus 2m times minus omega y vi. Okay. Now see, minus minus will become plus. So Fc will be equal to 2mv times omega yi. But you have learnt earlier that this omega y is equal to, omega y is equal to omega cos lambda. So Fc will be equal to this much. This is 2m omega v cos lambda I. This unit vector I, you know, is directed in eastward direction. So you can see that this Coriolis force acting on our body is directed in eastward direction. Mark it. Actually, you have dropped the body in the northern hemisphere. And so you can say that when a body will be dropped in the northern hemisphere, the Coriolis force will act on the body in eastward direction. And due to this Coriolis force, our body will get deviated from its original path in eastward direction. That will be the deviation. Deviation will be in eastward direction. But mark, this deviation will be in eastward direction only when the body will be dropped in the northern hemisphere. Actually, the direction of deviation will be just reversed when you will drop the body in southern hemisphere. So you can easily say if the same body will be dropped at a latitude from a latitude lambda from a height h in southern hemisphere, then this Coriolis force will be directed in westward direction, and so the body will experience deviation in westward direction, not in eastward direction. This is a very remarkable fact. Okay. Now, to find the deviation suffered by this body from its original position or original direction in eastward direction, we will write the equation of motion of this body in eastward direction. You have assumed that eastward direction is actually x direction, so you can also say that we will write the equation of the motion of the particle in x direction. And what is that equation of motion? Equation of motion means we will apply second law of motion. Mark it here. This Fx is the total force acting on the particle in x direction or eastward direction, and that will be equal to mass times acceleration of the particle in x direction, and this acceleration is due to the rotatory frame. But you know, in rotatory frame, two forces act on the particle. One is real force and another is the pseudo force. Pseudo force here is Coriolis force, and the real force is the force of gravity. So you have to take x component of the real force mg. This is this mg x represents the x component of mg, that is the x component of real force, and fcx means x component of the Coriolis force, which is a pseudo force, and that will be equal to m times d2x by dt square. Here x is actually the displacement or deviation of the particle in x direction, and you know, when x is differentiated one time with respect to t, then we get actually Vx, velocity of the particle in x direction. And when this Vx will be differentiated with respect to t, then we get acceleration. So you can say that actually the second order time derivative of x will give acceleration. So instead of ax, I have written d2x by dt square. But you know, gravity is acting in vertically downward direction, that is in negative z direction. Mg is acting in minus k direction. Okay, and your aim is to find its component in x direction, and you know, x direction will make an angle 90 degree. This angle does not appear 90, but this is 90. This is the three-dimensional case. In three-dimensional case, 90 degree angle does not appear like 90 degree because it is in negative z direction and we are finding its component in x direction. So angle between these two directions is 90 degree. So what will be the component of mg? This will be mg cos 90, and cos 90 is 0, so this will be 0. So the x component of the real force of gravity acting on the particle is 0. Okay, and you can see the Coriolis force is already in x direction. Here there is unit vector I, which represents x direction. So the x component of this Coriolis force will be simply equal to this much. This is 2m omega v cos lambda. So you can write 0 plus 2m omega v cos lambda equal to m d2x by dt square. Now m in both sides will cancel out, and you can write d2x by dt square equal to this much, that is 2 omega v cos lambda. But you know, when the particle is dropped from this point P and it is just to reach the Earth's surface A after covering a distance h, the time is t. It means we assume that the body is dropped at t equal to 0 and it acquires a velocity v at time t. So you know, from the kinematical equation of motion, V is equal to u plus gt. But u, which is initial velocity of the body, you know this is equal to 0. So you can write V is simply equal to gt. Okay. So at the place of V, now you can write gt. Okay, where g is acceleration due to gravity. So d2x by dt square, you can see now this is equal to this much. This is 2 omega gt cos lambda. Now solving this differential equation, our aim is to find x. But you can see, since here there is second order derivative of x and your aim is to find x, so definitely you have to integrate 2 times. When you will integrate to one time, then you will get dx by dt, and when dx by dt will be integrated, then you will get x. So definitely we will have to integrate 2 times. Now let us see. This d2x by dt square can be written as d dt dx by dt, and that will be equal to this much. This is 2 omega gt cos lambda. Now bring this dt here, okay? And so you can write this is simply differential of dx by dt. D means differential of dx by dt. And that will be equal to 2 omega g cos lambda t times dt. Now let us integrate it. And you know, we have dropped the particle from point P at time t equal to 0, and we are calculating its velocity at t equal to t. So the limit for time will be 0 to t. And you know, this differential will cancelled by this integral, because integration is the reverse process of differentiation. So differential of dx by dt, when integrated, that will give you dx by dt. So dx by dt, this will be equal to what? Since integral of t will be t square by 2, and this 2 and this 2 will cancel out. So after cancellation of 2, our result is dx by dt equal to what? This is omega g cos lambda t square. Okay. So after one integration, we have obtained dx by dt. Now when again we will integrate it with respect to t, we will get actually x, which is actually the deviation in x direction or displacement in x direction. And that is we have to calculate. Okay. So you can see from this result we can write dx equal to omega g cos lambda t square dt. Okay. Now again integrate it. Integrating dx and this t square dt, because omega g cos lambda is a constant factor, so it is outside of the integral. I have taken the limit for t 0 to t. Okay. And you know, when the particle will be just dropped, then that will suffer no deviation. So when t is 0, then x is also 0. So for lower limit for x is also 0. And we suppose when t is equal to t, that is the particle is near the surface of the earth, very close to the surface of the earth, then time is t, and we assume that at that time our particle has been displaced in x direction by x, we consider. So the upper limit for dx is x. Okay. Now you can see after integration what will be our result. In LHS you will write x, because integral of dx from 0 to x will be x, and integral of t square will be t cube by 3, and this 3 and this 3, sorry, no, here 3 will not cancel out. So there will be x equal to 1 by 3 omega g cos lambda into t cube. This is actually the deviation suffered by the particle due to the Coriolis force. You can see in this deviation there is no role of gravity, because the component of force of gravity in this direction is 0. So this deviation is only due to the Coriolis force acting on the particle. Okay, only due to the Coriolis force. Okay, but this deviation I have calculated here as a function of time. Now you can express this result as a function of height h, which is actually height of the point of dropping of particle from the surface of the earth. And that can be easily obtained because you know that if a particle will be dropped from here at t equal to 0, it covers a distance h, and here time is equal to t, and initial velocity of the particle is 0, then definitely you know the equation of motion h barabar ut plus half gt square. But in this case again u is 0, so this h will be simply equal to half gt square. Okay, so I have written here that this h is equal to half gt square, and so you can write t is equal to 2h over g whole to the power half. So in our expression we will replace this t by 2h over g whole to the power half. Okay, so expression for x in terms of h becomes 1 by 3 omega g cos lambda times 2h over g whole to the power 3 by 2. Okay, now this 2h over g whole to the power 3 by 2, this can be written as 2h over g times 2h over g to the power 1 by 2. Okay, now this g and this g will cancel out, and our result will be what? This will be x equal to 2 by 3 omega g cos lambda times 2h over g whole to the power half. This is actually our final expression for the deviation suffered by the particle or the body due to the Coriolis force acting on it in the Earth's rotatory frame. Okay, and you can see that this deviation, as I have told you earlier, is in eastward direction when the particle or the body was dropped from a point which lies in the northern hemisphere. Okay, so we can say that if the same particle will be dropped from height h in the southern hemisphere, then this deviation will again take place, but the direction of this deviation will be not eastward, but that will be westward. Okay, now see this expression seriously, and if I ask you that this deviation x depends on what factors, which are the factors affecting this x in the Earth's frame? If we are talking about Earth's frame, then this omega will be constant because the angular velocity of the Earth is constant. So x depends basically on two factors. What is the value of h? It means height of the point from where the body will be dropped. On that h, x will depend. And the another factor which is very remarkable, that is lambda, which is latitude of that place or that point from where the body will be dropped. So you can say that actually the deviation suffered by the body due to the Coriolis force x is a function of two variables or two parameters, h and lambda. Okay, now let us see the effect of this lambda keeping h constant. We keep h at a fixed value, and let us take some standard value of this lambda. You can see the figure here. This lambda is the angle made by the position vector of the point or place with the equator. So if this point P lies just above the equator, then this lambda will be 0. In other words, you can say that latitude of a place lying on the equator or just above the equator is equal to 0. On the other hand, if you are talking about a place or point which is on the poles, that is either on the north pole or on the south pole, then this lambda will become 90 degree. Or you can say that when our point will lie on the polar axis, then this lambda will be equal to 90 degree. Okay, lambda will be equal to 90 degree. Okay, yes. So we will see what will be the deviation suffered by the particle when it is dropped just above the equator and when it is dropped just above the poles of the earth. As you have seen that at the equator or just above the equator, lambda is 0. And when lambda will be 0, cos lambda will be 1, which is its maximum value. So as cos lambda will be maximum, so whenever the body will be dropped from a point just above the equator, it will suffer maximum deviation. Maximum deviation. So I have written here that in this case deviation x is equal to xe, E for equator, and that will be equal to x max, and that will be what? We will simply put cos lambda equal to 1, and so the expression will become 2 by 3 omega h times 2h over g whole to the power half. This is actually the maximum deviation suffered by a body when it is dropped from a height h above the surface of the earth. Okay. Whenever it will be dropped from any other point, deviation will be smaller than this value. This is the highest value. Okay. But if you drop the body just above a point lying on the north pole or the south pole, then what will happen? For this point P, which lies just above the poles, lambda will be 90 degree, and so this cos lambda will be 0. And if cos lambda is 0, you can see this expression that this x will vanish, x will be 0. So a body will suffer no deviation when it is dropped from a point above the polar axis, or you can say above the pole of the earth. In this case, there will be no deviation. So these are two very remarkable points. For different places, when the body will be dropped from same height, deviation suffered by the body will be different, because for different places lambda will have different value, and due to the variation of lambda, the deviation x will vary. Okay. So I think definitely you have enjoyed this lecture, because this was a very simple concept and it is very important for your examination purpose. Okay. Now in the forthcoming lecture we will see another important application of this concept, and that will be actually regarding the variation of acceleration due to gravity due to the centrifugal force acting on our body. Okay. So wait for my next lecture on variation of acceleration due to gravity. Thank you very much.